Everyone. Hello everyone. So we're going to go back to Calc AB review. Going to be revisiting solid of revolutions today with calculus. And so basically a solid of revolution is when, say you have a function, let's just use a function like that. Let me clear this up so it's easier to see. Sorry about that. There we go. And so let's say we have this function here. And of course we have, let's make an upper limit. Let's say this is y equals 8, and this is going to be x equals 2. So it's bound by the x-axis and the graph of f here and x equals 2. So we're going to be talking about this region right here. And so what happens with a solid of revolution is, if we're going to take it around the x-axis like this, we're going to rotate it. This is going to make some 3D shape like that, which we could now take the volume of. Vice versa, if we had another function, let's just make two functions. Here we have one like that, and we have one like that. They're at A and B. Or here, let's just simplify that. We'll make that the y-axis. So that's x equals 0. Actually, it should be A and B. Sorry about that. A and B. So you can see those are the intersections of those two graphs, and we're looking at the region right here. Let's say we're rotating this thing around the y-axis this time. I'm going to rotate around here, and that would make something that looks like this to form. So we have something like that. Okay, so basically that's a visualization of it, but now how do we solve something like that? Let's go back to our first example here, and we're going to actually use this equation, pi times the integral of a to b, and there's two ways we could do this now. For ones like this where there's no hole, there isn't a hole when we have this solid revolution, it's just going to look like something like this with no hole. We're going to use the disk method, which is radius of that new shape squared dx, and vice versa. We'd put ry dy if it was over the y-axis. Okay, so with this one, this is called the disk method again. We just need to know that radius. So how do we find the radius? So we redraw the graph just simply with the graph like that, nothing fancy. And if this is our axis of rotation, then the radius would be this line. Would be this line right here. Would be, so if this is our region, again, if this is our solid of revolution, this length right here would be our Rx. Okay. So now we could do also the washer method. Washer method is when there's a gap in between. So other versions of this would be if there's a hole and there's two functions here and you're rotating them, there's still that hole around an axis like that. And also if we have something, let's say if we had that same function right here, and then this is y equals 8, and this again x equals 2, this line right here, and we're going to revolve it around y equals 8 like that. So then we would have this shape kind of like this. I'll draw it better here. Kind of has something like this. Okay, and how are we going to find this is y equals 8? Now if we notice on this figure right here, we have actually a hole, and then we also have this outside area. So we have this, we also have this hole here, which is a smaller unit, because see, this space is inside while we have the actual outer area. So actually, if we took sections, it would have this hole. It's like a donut. This is called the washer, and we use the washer method when we're dealing stuff with that. Washer method is very similar. It's just has an extra piece in it. So pi times the integral of a to b again of r x squared minus, see, this is our inner radius here, so we need to take this outer radius minus our inner, just that whole, minus rx squared dx. And again, place the x's with y's if you're rotating respect to rotating it by a y equals, or an x equals, or the y-axis. Okay, so now we can look at